Hello everyone, myself Konda Krishnudu, Assistant Professor of Physics, Department of Science and Humanities, MLR Institute of Technology, Hyderabad. In the previous class, we discussed about direct and indirect band gap semiconductors, the differences between them, as well as finally their applications. Today, in continuation to that, we are going to discuss about Hall effect. So coming to overview of today's presentation, today I am going to talk about introduction, construction to Hall effect, and working, derivation of Hall coefficient, applications of Hall effect, and finally conclusion. So coming to the introduction and construction, first of all we should know what is Hall effect. So Hall effect, the name derived by the scientist E.H. Hall. So E.H. Hall is the scientist who studied for the first time about this phenomena, and hence after his name it is called Hall effect. So particularly this is applicable both for conductors as well as semiconductors. We know in the case of conductors, charge carriers are only free electrons, whereas in the case of semiconductors, charge carriers are both electrons and holes. So this Hall effect or this phenomena is applicable for both conductors as well as semiconductors. So first of all we should know the basic definition of Hall effect, or what is Hall effect. So Hall effect, when a magnetic field is applied perpendicular to a current carrying conductor, voltage will be developed in a direction perpendicular to both electric and magnetic fields. When magnetic field is applied perpendicular to a current carrying conductor, voltage will be developed in a direction perpendicular to both electric and magnetic fields. That is what is called Hall effect. And the voltage so developed, which is perpendicular to both electric and magnetic fields, is called Hall voltage after its name. And this is the experimental setup through which you can understood the basic definition of Hall effect. So one semiconductor slab we have taken here. This is semiconductor slab having 3 dimensions. We know the 3 dimensions are its length, its breadth, and its thickness, right? So length of the semiconductor slab we have considered along x-axis, and its breadth we are considering along y-axis, and its thickness we are considering along z-axis. So this is the semiconductor slab which we have taken, and current, as per this, current is flowing along x-axis. Current is flowing along x-axis. For this we have applied magnetic field along z-axis. Magnetic field is applied along z-axis. What happens when we apply magnetic field perpendicular to this current direction? As per the definition, voltage will be developed. Voltage will be developed in a direction perpendicular to both electric and magnetic fields. This is y direction where the Hall voltage will be developed, which is perpendicular to both the electric and magnetic field. So that is how we need to, or we should understood the basic principle of the Hall effect. So in the case of semiconductors, there exists 2 types of charge carriers. Our conductivity in the case of semiconductors is due to electrons as well as holes. So which is the principle involved in this case, so that voltage is developing in a direction perpendicular to both electric and magnetic fields, that we need to study. So that we can understood from this slide. On a charge carrier, 2 types of force will act. One is force due to electric field and another one is force due to magnetic fields. 2 types of force acts on the charge carriers which is inside the semiconducting slab. The first one is due to electric field. So due to the applied field E, the force acting on the charge carrier is considered as small q into E. Force, this is due to the applied electric field, where q stands for charge. It may be either electron or hole. If it is electron, that the charge is taken as negative. If it is hole, that charge is taken as positive. Next, coming to the force on the same charge carriers due to the applied magnetic field. So force due to magnetic field is considered with this equation. F is equal to Q into V cross B, where Q is nothing but again here the charge carrier. If the charge carrier is electron, it is taken as negative, and if the charge carrier is hole, it is taken as positive. So like that, two types of force acts on the charge carriers in this case. Now, before going to discuss or before going to derive expression for Hall coefficient, now we need to know due to the force on which direction the charge carriers are moving. So that we can understood from these two pictures. Here, consider the first case. Q is equal to plus E means positive charge we have taken. This positive charge is moving. So when positive charge is moving along x direction, then this positive charge will experience downward force. This positive charge will experience downward force, and the same when we consider in the case of negative charge, the force will act upwards when this is upward. Charge carriers will experience upward force when they are negative charge. Okay, so that is how charge separation is taking place. Charge separation is taking place. On one side, negative charge is accumulating. On the other side, positive charge is accumulating. Because of this accumulation of charges, voltage is developing. Now, coming to derivation of Hall coefficient. So, to derive Hall coefficient, just now we discussed that two types of force acts on the charge carriers. One is due to the applied electric field and the other one is due to the applied magnetic field. So, when these two forces are equal, when they are at equilibrium, then we have to equate those two forces. This is the expression for force due to applied field, and this is the expression for due to the applied magnetic field. So, under equilibrium condition, both forces are equal, and by doing so, finally we will get one expression. So, this is the expression we are going to get, minus 1 by Ne equal to E suffix y by J suffix x B suffix z. So, what is Ey here? Ey is nothing but electric field or voltage which is created along y axis. Jx is nothing but current density along x axis, and Bz is nothing but magnetic field along z axis. So, current is flowing along x axis, magnetic field is applied along z axis. As a result of that, voltage is developed along y axis. So, based on this, finally we will get one expression, minus 1 by Ne equal to Ey by Jx Bz. Now, so Hall coefficient is denoted by capital R suffix H. Hall coefficient is negative for electrons. It is negative for electrons. Hall coefficient is taken as positive for holes. Okay. So here, finally, using above expression, we can write Hall coefficient with this equation as minus 1 by Ne. This minus 1 by Ne we are going to replace with RH. So, using this symbol for minus 1 by Ne, we can write finally RH or Hall coefficient equal to Ey by Jx Bz. Now, we are going to derive expression for Hall coefficient in terms of width of the sample as well as thickness of the sample. So, let us consider that B is the width of the sample across which Hall voltage is measured, right. If that is the case, electric field along this is taken as EH equal to VH by B. Electric field EH equal to VH by B. We know one standard expression, V is equal to ED. Voltage equal to electric field into distance. So, using this we can write EH equal to VH by B. Now, taking Hall coefficient expression, RH equal to EH by BZ. Okay, now using this, we are going to replace EH with VH by B. EH equal to VH by B. So, this expression we are using in the place of EH, so that we will get this and write VH. Finally, VH is taken as RH into BZ Jx into B, where B is width of the sample. Now, so now we are going to take Jx. Jx is nothing but current density. Current density is nothing but current per unit area. current density is taken as current per unit area, so that Jx we can written as current as Ix by unit area. Unit area is taken as product of width and the thickness. So using this expression here in this equation, we get VH as like this. So VH equal to, actually RH Bz Ix into B. Now I am going to use Jx in this equation. RH Bz Jx, in the place of Jx I have to write Ix by Bt into B. So B will be cancelled here, and finally VH is equal to RH into Bz Ix by T. So from this expression we can write RH. So RH is nothing but VH T by Ixb. So RH equal to VH T by IB. RH equal to VH T by IB. Current is along x-axis, magnetic field along z-axis. So by knowing the values of thickness of the sample, by knowing the value of current which is flowing across the length of the sample, and magnetic field Bz which is applied along z-axis, and the value of Hall voltage which is produced, by using all these values we can measure Hall coefficient. Actually all these values Ix, Bz and T will be there, and finally we are going to measure Hall voltage which is produced as a result of Hall effect across y direction, and using this value along with the existing values of thickness, current and magnetic field, we can determine Hall coefficient, that is RH. That is expression for RH in terms of thickness. So far we discussed what is Hall effect, and for which material it is applicable, and what happens when force acts on the charge carriers, that is separation of charge carriers take place. As a result of that, voltage will be created, and that we discussed in terms of Hall effect. Finally, what are the applications of Hall effect? So Hall effect has so many applications. First of all, coming to its very important application, it is used to determine whether a given semiconductor is of p-type or n-type. So we know extrinsic semiconductors are of two types, p-type and n-type. So after doing experiment, we are able to determine whether a given semiconductor is p-type or n-type. So after doing experiment, if we get Hall coefficient as negative, then we can say that it's n-type semiconductor, and if Hall coefficient is positive, then we can say that it is p-type semiconductors. That is the first and foremost application of Hall effect. We can determine the type of semiconductor, whether it is p-type or n-type. The second one is, it is used to find the carrier concentration. So we know Hall coefficient RH is given by one expression, minus 1 by Ne. It is for electrons. If it is for holes, we can written as like this, 1 by P into E, where N is the number of electrons and P is the number of holes. So in both the cases, suppose for example for electrons, we can written as N is equal to 1 by RH into E. Simply by substituting the value of RH, we can calculate small n, that is concentration of charge carriers. That is, in the case of n-type, the number of electrons, in the case of p-type, the number of holes. Carrier concentration we can calculate provided the value of RH is known. That is one more application. And Hall effect is also used to find the mobility of charge carriers. So what is mobility? Mobility is nothing but the ease with which charge carriers are moving inside a semiconductor. When we apply electric field, charge carriers will move under the application of that due to force acting on them. How much fast they are moving, the ease with which charge carriers are moving under the presence of applied field is called mobility. So mobility is related to conductivity with this equation, sigma is equal to Ne mu. More is the mobility of charge carriers, more will be the conductivity of that sample. So using this equation, we can write mu E is equal to sigma by Ne. Sigma by Ne, and here 1 by Ne is there. So this 1 by Ne we can replace with RH. So that finally mu we can written as sigma RH. So finally mobility of the charge carriers can be calculated using the value of Hall coefficient. Mu E for either electrons or holes, we can calculate the mobility. So that is one more important application. And finally, the most important application of Hall effect is that they are used in magnetic flux meters. They are used to measure minute magnetic fields using this equation. So using the values of thickness, current and Hall coefficient, also the Hall voltage which is produced during the experiment, we can calculate magnetic flux. Okay, now, so that is why they are used in magnetic flux meters. So in continuation to previous slide, these are some more applications. So generally Hall effect is mainly used in sensors. So many will be there. One is to measure magnetic field sensing equipment. So they are used to measure magnetic fields accurately. So instead of traditional methods, if you use Hall sensors, we are able to determine magnetic fields to a high degree of accuracy. Coming to the second application, they are used to measure current sensors. They are used in current sensors. So by using current sensors, we can measure electrical currents without direct contact with the equipment. Without direct contact with the equipment, we can measure the current if we use Hall sensors, Hall current sensors. So by that, safety and reliability will be there with the electrical systems. The third one is voltage sensors. So Hall voltage sensors are used to measure voltage across different systems, and voltage will be measured precisely and accurately when compared with the traditional methods. And finally, magnetoresistive sensors are also there. So where the magnetic field will be changed with respect to the resistance, or with respect to resistance, magnetic field of the material will change. That is what is called that magnetoresistance property is used in magnetoresistive sensors. So in all these devices, what I have mentioned here, so Hall effect is used. So like that, Hall effect has so many applications. So that's all for today, where we discussed what is Hall effect and who devised or who studied extensively about the Hall effect. It's a basic definition, the construction of Hall effect, as well as the working principle, and then the derivation of Hall coefficient, the general expression, as well as Hall coefficient in terms of breadth and thickness of the sample. And finally, we discussed applications of Hall effect. So in continuation to this, in the next class, we are going to discuss about various optoelectronic devices. So many optoelectronic devices are there, which are capable of converting either electrical energy into optical energy or optical energy into electrical energy. So one of such optoelectronic devices we are going to discuss in the next class. Thank you.